and welcome back to Phi-Sci, and today I would like to discuss about this problem of compound pendulum. Compound pendulum is doesn't have a bob and a string, so point is not concentrated in the bob, it is distributed over a length of rod. So that is what a compound pendulum is. So we will find a Lagrangian today. So as we know, Lagrangian is basically L is equal to T minus V, where T is the kinetic energy, and V is the potential. So considering a evenly distributed rod or some kind of shape as the compound pendulum, we take the shape as omega. Omega is basically the shape of the compound pendulum. And we need to find the mass. So mass, let's say rho is basically the mass density. Okay, so we need to find the mass of this compound pendulum, which is basically nothing but the integration over the entire shape with rho as a function of p, and the integration over the entire mass density over the shape of the compound pendulum. And here we need to find the center of mass. Center of mass is basically the inverse of the mass of the same thing, basically. Sorry, it is basically this. Over this shape. Now the difference in a bob and string pendulum and a compound pendulum is the moment of inertia. So here we need to consider the moment of inertia as a point on the pendulum. Okay, so considering the moment of inertia from a point mass on the pendulum, we take the integration over this rho, the mass density, and say L. Here L, I should say, is the length of the point mass from the point of origin. Okay, point mass from the point of origin, which say the moment of inertia through which about which the pendulum is swinging. So we take this as a pendulum which is swinging, and then we just write it like this. Here L is the length, okay, the length of the point mass on the pendulum. And P is the distance, and here this modular square of the P is basically the distance from the origin of. We just compute this from L to here. Okay, so there is not a dot. Okay, this is not a dot, and the distance from origin. So we get the moment of inertia. So in order to find Lagrangian, we need to find the kinetic energy. So in order to find the kinetic energy, we know the kinetic energy formula, which is basically half mv square. Here velocity square is nothing but angular change, so we consider mass we know, which is half integration of rho as a function of p, and velocity square is basically delta t square. Okay, and we have already found that the moment of inertia is supposed to change because we are considering the point mass. So here this will be this will not be the mass, but the moment of inertia, the point mass that we are considering for the change. Okay, so here it will just compute to half I theta dot square. Okay, and also we need to find the potential energy, which is U, or we can say V, and which is nothing but basically mgh about the center of mass of the pendulum. Now center of mass of the pendulum, and this body is the compound pendulum being evenly distributed mass over all its body will rotate at an angle of theta at the point of center of mass. So we come to the conclusion, we can write it like this. Okay, and then just put this in this formula. Basically we can say this is nothing but T, and it comes down to half I theta dot square minus m g h e I theta c. C here is the center of mass, I is the moment of inertia.